Avogadro's law basically states this: equal volumes of ideal gases contain the same number of molecules at the same temperature and pressure. And so, in a sense, what we're saying is this: if I have 1 liter of carbon dioxide at, say, STP, then the number of molecules in there, if you were to count every molecule of carbon dioxide in that 1 liter, you'd find the number of molecules in that 1 liter of carbon dioxide would be exactly the same as the number of molecules of hydrogen gas in 1 liter at STP, or the number of molecules of oxygen gas in 1 liter at STP. And so basically what it means is that if you have two equal volumes at the same temperature and pressure of different gases, you know they have the same number of molecules in them. This actually turns out to be the way they actually were able to discover that the atom existed, was by noting the fact that that equal volumes had the same number of molecules in them, or that whenever they reacted gases, that they came out exactly in whole number ratios, based on this law right here. But if this is true, and where this becomes important to us, is that if it is the case that any volume of gas, no matter what the gas is, contains the same number of molecules, then it means that if I have 1 mole of a gas, that's how many particles I have, that mole would occupy the same volume as any other gas under the same conditions. Obviously, if I have one gas that's at 760 torr and another gas that's 830 torr, they might have different numbers of moles in them. But if I have them in the same conditions, then 1 mole of any gas occupies the same volume as any other gas. The term for this volume, the volume of 1 mole of a gas, and it can be any gas based on Avogadro's law, is called the molar volume. This molar volume, we can calculate it for any temperature and pressure. And so at 300 Kelvin and 800 torr, we could find the molar volume of a gas, the volume of 1 mole. Usually, though, the most useful one to find here is basically what we're going to find is at STP, because that's the conditions we sort of want to bring things to. And so the molar volume of a gas at STP is 22.4 liters. It's what we're going to sort of say it for this class. Sometimes you'll see it out for a few more decimals than what you've got right there. But overall, this is it right here. So at STP, molar volume of a gas is 22.4 liters. So if I have 1 mole of hydrogen gas at STP, it fills a volume of 22.4 liters. If I have 1 mole of methane gas at STP, it'll fill 22.4 liters. Doesn't matter what gas it is. If it's at STP and there's a mole of it, it's going to have a volume of 22.4 liters. That's basically how Avogadro's law works. So let's take a look and see what we would do with this. Gas stoichiometry, which is basically what we're talking about this unit, is based on this fact. This fact that we can find the molar volume of a gas is going to let us do conversions between one gas in a reaction and a different gas in a reaction, using basically the same stoichiometry principles we talked before. And so gas stoichiometry is a method of calculating the relationships of reactants and products when reacting or producing gases. And so we have done stoichiometry in the past, where basically we said, I've got this many grams of this thing and this many grams of this thing, and I react them together, and I can figure out, based on that, how many grams of the products I get. In this case right here, let's assume that we're putting 2 gases together. We mix oxygen gas and hydrogen gas and light them on fire. When we do that, we're going to end up with water vapor. And so if I were measuring this out, typically if I were measuring an amount of oxygen gas I'm adding, it's very difficult to measure that in grams. It's very sort of hard to take the amount of oxygen gas and put it on a scale due to mostly the issues of the buoyancy of the air that surrounds it. But it's very easy to measure the volume of that gas. And so typically if you're reacting gases, you're going to be measuring their volumes. And so if I was going to do a stoichiometry calculation to figure out how much of my products I'm going to get, I would want to start with the number of liters of that gas, not the number of grams of that gas. And so in gas stoichiometry, basically it's going to deal with this idea of converting from volumes of gases into moles. Once we've converted from volume into moles, then we can basically go from moles to anything else we want to in the same principles we've used in stoichiometry previously. And so, in a sense, is that, we said before when we were talking about stoichiometry, is that sort of moles is what we're trying to get to. That's sort of our grand central station of what we're trying to get to here. And in the past, we've talked about how to get from mass to moles, and we've talked about how to get from number of things to moles. And basically what we want to do in those cases is, if we want to go from moles to mass, we're going to use the atomic mass or the molecular mass. And so that's what we'd use to basically go between moles and mass in here, atomic mass and molecular mass. If we want to, and of course do the same thing to go from mass to moles. If we want to go from moles to things, then we're going to use Avogadro's number, 6.022 times 10 to the 23rd. Also works to go from things to moles. Now our new one here is that if we want to go to a volume, we can similarly go from volume to moles. Now, how we get from volume to moles is going to be what we're going to talk about in these next two sections. This amount that we're going to use here is that if the gas is at STP, and we want to go from volume to moles or moles to volume, then we see it's sort of underneath my drawing a little bit here, but at STP, the molar volume of a gas, 2.4 liters per mole, can be used to convert from moles to liters and vice versa. So if I have a gas that's at STP, and I know how many liters I have of that gas, then I can find how many moles I have pretty easily just by using 22.4 as a conversion factor. And then once I've got from volume to moles, I can then use volume to moles to go to mass or go to number of things or anything else I want to go to. I can do a mole ratio to a separate substance if I have a reaction. All those things, all those tools that we had in stoichiometry are available to us. So if we're not at STP, we know this. We have the molar volume of gas is 22.4 liters. So that's 1 mole fills up 22.4 liters when it's at STP, but only at STP. If the temperature is any off, if the pressure is any off of STP, you cannot use 1 mole equals 22.4 liters. So if the gas is not at STP, we have to use instead the ideal gas law. And so the ideal gas law must be used to convert from volume to moles and vice versa. And so that's our good friend, PV equals nRT. This then, if I know what the volume is and I know what the temperature is, and I know what the pressure is, if I know what the pressure is and know what the temperature is, lets me convert between the volume and the number of moles. And so that's what we're going to look at here. So in this case right here, we start off with a case where we say 6 liters of ammonia is decomposed into hydrogen and nitrogen at 850 torr and 350 Kelvin. How many moles of nitrogen are released? And so first step on these is it's still a stoichiometry problem, so we still got to balance out our chemical equation here. And so in this case, we have a decomposition reaction of ammonia. Ammonia is one of those that you just sort of need to know what it is. It doesn't fit our naming rules, but you just need to know it's NH3. And it's decomposing, so it's coming apart, and it's turning into hydrogen and nitrogen. So hydrogen gas is H2, nitrogen gas is N2. And so we're going to balance this guy out. Right now we have 1 nitrogen on the left and 2 on the right. And so that means I have to put a 2 out in front of the NH3. That gives me 6 hydrogens on the left and only 2 on the right, so I have to put a 3 out front there. And that should have that balanced out, so 2 NH3 yields 3 H2 plus N2. So what we start with here. So let's see what we got here. We have 6 liters of ammonia decomposed. So we start off with 6 liters. So I have 6 liters of ammonia. So 6 liters of NH3. I normally would go ahead and set up my table, and I would say liters of ammonia to moles of ammonia. But the problem is with that is it isn't an STP. No, it's not. It's 850 torr and 350 K. And so in this case right here is that I really don't want to use this method right here. That's not where I want to go. And so we'll have to wait for the bell whenever it comes, and there we go. And so based on this, instead of using this because this is not STP, I am going to have to use the the ideal gas law to figure out what my conditions are here. And so I say I've got PV equals nRT. My pressure in this case is 850 torr. That's an 850 torr times the volume, which we say is 6 liters. 6 liters equals N, which is what I'm looking for, times R, 62.36, times T, the temperature, which is 350 K. Okay? And so doing this, I can go ahead and you can solve for the number of moles. And so in this case right here, to get that, we'd say 850 times 6 liters. And then we got to divide by the 62.36 and the 350 to get this to work. So divided by 62.36 and then divided by 350 Kelvin. And so in this case that we get that our number of moles, our N, is equal to 0.2336667, right about there, moles of ammonia, because we started off here with, it's NH3, not NH4. As we started off here with liters of ammonia, so this gives us moles of ammonia. Well, once we have moles of ammonia, we can now go ahead and set up our problem the same way that we did before for stoichiometry, is that we started up with, we said 0.23366627. I guess I probably should have didn't round that right earlier. But this is moles of ammonia, NH3. Set up my table the same way I did before. I want to go from moles of ammonia to what I want, which says how many moles of nitrogen are released. So we want to go to moles of nitrogen. So N2. So in this case, we look up at the top. We say, how many moles of ammonia do we have? There's 2 is our coefficient up there. How many moles of nitrogen? Nothing out there, so just a 1. And so in this case right here, we set this up and solve. We get our number 4.2336667 times 1 divided by 2. And so in this case right here, we get, I guess actually this one right here should have, based on our numbers here, this has 3 sig figs, this has 2 sig figs, that has infinite sig figs is written out. So our answer should have 2 significant figures. So 0.12 moles of nitrogen would be our final answer. And so that's how we finish that up right there. So you can sort of see what we do in this case of a gas that's not at STP. Basically just take it, set it up, write out the equation, and then once we've done that, we want to find the number of moles by using PV equals nRT, ideal gas law, because we can't do the 22.4 thing because it's not at STP.